Okay, two of these. Okay, now first of all, we're trying to solve an equation, right? So we're going to solve this polynomial equation. What do I do when I've got big equations like this to solve? What's my cry? No. Once you're done crying, what do you do then? What's our strategy always? Okay, good. Now we're gonna factor it. We always goal, and I don't want to see any phones and stuff. I don't want them on your desk. I want them in your pocket, away completely. Don't want to see them. Okay.
Really a sketch of, so.
Okay. So yeah, when we've got big polynomials like this, and even if they're quadratic, what we did, well, actually, if they're quadratic, we may not need to, because then we could use the quadratic formula to solve this. But if I've got bigger than quadratic polynomials, and I'm trying to solve this equation, it's hopeless for me to sit here and try to just find values of x that are going to make this thing go to 0. I mean, there may not even be any, right? It's possible that there won't be any real numbers, for example. Maybe I'm looking for real solutions. What I have to do is I have to use my strategy of factoring and zero product property. I got to break this big 4th degree polynomial up into a product of smaller pieces, smaller factors that I could individually set equal to 0 and solve. If I can get them down to where they're quadratic or smaller, that's great. Because then all of those factors I could set equal to 0 and solve. Linear ones are just a gimme, right? Solving linear equations is just isolating x as a piece of cake. 2 steps and you're there. If it's a quadratic factor, I can deal with those too. Either by, in some cases, isolating x, or at the worst case scenario, just quadratic formula, right? But I can't do, there is no magical formula bigger than the quadratic formula. So if it's cubic or quartic or bigger, I got to break it into smaller pieces. Now the first step is always, when we're factoring something, we always want to see if we can factor out a greatest common factor. Okay? Is there a number that divides into all those numbers? No. But they all have an x, don't they? Yep. Right? I want to factor out the weakest power of x of all the terms, because in this case they all have powers of x. So what's that going to be? X to the 1. Good. So I could factor out or undistribute an x. Now I think I would definitely recommend that you write the leftover then. Once you factor the x out, write the leftover factor in brackets, because there's still going to be a lot of work to do there, right? But we want to be able to separate it. This one's done. The greatest common factor is out front. It's done. What are we left with if I factor out an x? First term gives me 3x cubed. Good. Second term gives me 9x squared. Third term gives me 2x. Good. Last term gives me minus 6. Okay. So now in the brackets, that's better. It looks a little better, but I've still got a 4-term polynomial. So what's our new strategy? If I've got an even number of terms in a polynomial, and we're going to restrict ourselves to 4 in this class, what do I do? No, that's different. Synthetic substitution would be, that's if we're trying, not if we're solving something. If we're solving, that's if we're trying to evaluate a polynomial for a certain value of x. But if we're trying to solve for x, it's got to be a factoring strategy. What's our factoring strategy with 4 terms? Okay, I'm going to factor by grouping. I'm going to group it into 2 separate groups of 2, right? And so now I want you to watch this very closely, though. When we work down, this is something you guys need to get a little bit better at. And it's getting to the point now in algebra where you can't just finesse it anymore. You're going to have to start doing lots of work. I mean, this tendency will only grow. When you get to calculus, some of the problems we're doing in calculus now take, pages of work for a single problem. And I couldn't sit down. I've done a lot of math in my life, but I could not sit down and do one of these calculus problems without writing a bunch of stuff down. I would just confuse myself and I'd make mistakes and be really frustrated. And so I would never hope my calculus students could, because they haven't had that much practice. So they have to write the stuff down. Well, it's getting that way for you guys a little bit now too. A problem like this, there is no way you can just kind of scratch out a little work on a Post-it note or something. I mean, this is where you got to really kind of organize your work a little bit and write some stuff down. So now, when you're doing algebra, you know, when you do hard algebra, it really gets to be important that you keep it organized. And the way it's a very simple process when you're doing work on a piece of paper. You pretend this is a piece of paper. You just make a new line on the paper for every algebra step. That's all you do. So here we factored out an x, got a new line. Now we're going to do something else. The x is done, but inside the brackets, I'm going to split this up into two groups. Right? So it's going to look like this. First group plus second group. First group is just that, right? 3x cubed plus 9x squared. Second group is that, negative 2x minus 6. Okay, and now we're going to do our grouping pattern. And you even know what the template's going to look like. And when I say that, I think that's actually a really important thing to think about. If we know what the template is going to look like, it means we know what the form of the algebra is going to be. We have to just find the specifics. When I factor by grouping, give myself plenty of room here. We always know what happens. This first group, I'm going to get a greatest common factor, right? And I'm going to have a leftover factor. Plus, same thing in the second group, right? A greatest common factor and a leftover, right? And it may or may not work, but if it works, that's how it's going to work. If it doesn't work, we can't do the problem. And we just, you know, it'd be unfair. You have no strategy. This is it. There are other things later that you learn how to do, but for now, this is it. So what's the greatest common factor from the first group?
3.
Okay, good. I got to look at the number part and the variable part. The number part is clearly a 3. The biggest number that divides into 3 and 9 is 3. They both have powers of x, so what's the wimpiest power of x? X squared. So I can only take an x squared from each of those two, right? Now what am I left with if I do that? If I factor that out or undistribute it, what do I get from the first term? X. Oops, blue. Second term?
Plus.
Yeah, plus 3. Everybody see that? Okay, so now here's another thing that's really important. That is a procedure, but it's very strategic. I know that if factoring by grouping is going to work, that has to be an x plus 3. It has to. Otherwise, factoring by grouping just can't work. So the question is just then, we can go ahead and put that there, but the question is, can I factor something out of those two terms that would make that my leftover? If I can't, I'm done. Can't do the problem. But I could. I could take out a negative 2, right? And my suggestion to you is, see what would work for the first term. Well, it needs to be a negative 2 to make that a negative 2x, and then just test it in the second term. Negative 2 times 3 is negative 6, so it checks there and there. Yeah, it works. So it factored by grouping, right? Okay, now all we have to do is just clean that up. We broke it apart, we did the grouping, and so now this will actually help you understand factoring by grouping this problem. I think having that extra factor x that's already been factored out front actually makes this easier to kind of visualize and understand. All we're going to do is the stuff inside the brackets. Look, I've got two terms. I've got term number 1. Terms are things that are added or subtracted, right? So I've got term number 1 and term number 2, and those are being added, right? I want to see, is there a greatest common factor there? Is there a common factor in each term? Well, yeah, x plus 3, right? X plus 3 is a factor in each of those two terms, and so I can factor that out front with the x. Everybody see that? I can pull that out front also. So then out in front, I'm going to end up with x times the quantity x plus 3, and then what's going to be left over inside of our brackets? If I factor out that x plus 3, what's left over in there?
Minus 2.
Yeah, 3x squared plus negative 2, right? Okay, is everybody getting this? I just feel like there's a pocket of people that aren't really getting this, and they're not helping us out. So if you're not going to try to get it, just go to lunch, get out of here. Okay. So first term gives us a 3x squared, so, and then plus negative 2 I could just write as minus 2, right?
How did the x plus 3 get on the half side?
Because look, I've got this, inside the brackets, I've got this first term. The first term has two factors in it, but terms are things that are being added. I've got all this stuff plus all that stuff.
Okay.
When I'm factoring out a greatest common factor, what that really means is I'm gonna find the biggest factor that's common to each term, right? So for example, up here, if I back up a little bit, look, I've got 4 terms up here, and the greatest common factor was x. That's the only factor of each of those terms. The only thing that was being multiplied by something else in each of those 4 terms, right? So we're doing the same kind of thing down here now.
Okay.
We've only got 2 terms, but the factor that's common to both is the x plus 3, so I'll just factor that out front with the x, leaving me with 3x squared plus negative 2, or just 3x minus 2. 3x squared minus 2, sorry. Okay, so then this, look what we've got here. We got this thing boiled down now to a product of 3 terms. I've got, or 3 factors, sorry. X times x plus 3 times 3x squared minus 2, right? So that's a lot. We accomplished a lot there. We took this big, ugly 4th degree polynomial expression and we broke it apart into 3 separate factors, a product of 3 factors. Each of those 3 factors is quadratic or smaller. And so now we're prepared to set them equal to 0 and solve, right? Did I get that? Yeah, I did. Yeah, okay. So let's do that, right? It's fully factored. If I set the first term, or the first factor equal to 0, what's my solution? 0. So I get x equals 0. Or, what's the solution to the second factor? Negative 3. Or, now the third one's a little bit tougher. The third one, we've got to do a little bit of algebra here, right? So I'm going to get, if I set 3x squared minus 2 equal to 0. Okay, you guys, listen. I'm looking back there and I'm seeing a lot of people with really bad grades that aren't paying attention. You guys, up here. Osias, get up here. DJ, why don't you come up here and find some place too. Go someplace else. That's not a good spot for you. Grab one of these desks. How about it? Okay, so then we got 3x squared minus 2 equals 0. What do I do to solve that? Very simple. What are the 2 steps I'm going to do?
Plus 2.
Add 2 and then divide by 3. Let's stop there for a second. If I do that, I get x squared equals 2/3. Now what? Square root. So my final answer then is x equals
Square root of 2/3.
almost, not quite. Forgot something. Plus or minus, because there's 2 answers there, 2 solutions. Plus or minus square root of 2/3. Okay. So I got 4 answers out of that, right? That big problem gave me 4 solutions. X equals 0, or x equals negative 3, or x equals square root of 2/3, or x equals minus square root of 2/3, right? Okay? All right, so that's how we deal with those. Now, another one. Okay, what if we're supposed to, this is a tough one. We did one last period. I did this very problem, but I made it easier because we were solving the equation, when does it equal 0? And when we get to that point in the problem, I'll tell you why they caught a break. That was a little easier problem. If I'm supposed to factor this, that's a little harder to do because factoring it, sometimes it's easier to solve a quadratic equation than factor them. You'd all agree, probably, right? Factoring them is sometimes a little tougher. Now I got 3 terms here. Can I factor out a greatest common factor? Is there a number that goes into 6, 5, and 6? Nope. And then I can't pull out an x because this last term doesn't have any x's, right? So I'm stuck with that the way it is. I've got to factor this thing. But I got 3 terms. Now the goal here is, only strategy we have is, can I fit this into a chapter 5 quadratic pattern? And we can. In chapter 5, what we were used to seeing is something a little different. In chapter 5, we got a lot of problems like this. Our problems looked like a times some variable. I'm not going to call it x because we have x's up here. Let's call it something like, how about u? So au squared plus b times u plus c, right? Where u is our variable. Typically it was an x, but it doesn't have to be. right? That's our quadratic pattern. A times the variable squared plus B times the variable plus the constant C. Now, what's our A, B, and C? If I want to try to fit this red pattern to our original equation, what's A? 6. What's B? What's C? Okay, here's the tricky one. What's U? No. X squared, exactly. U is like x squared, okay? So we could take this original pattern and we could write this as 6 times x squared squared. Whoops, want to be black. Whoa. Right? Because that's x to the 4th, right? Minus 5 times x squared minus 6, right? And now that looks like a quadratic pattern. I've got A times something squared plus B times the variable plus the constant C, right? Now factoring that is not a lot of fun because A is not equal to 1, right? And you see why this would be an easier question if we were just setting this equal to 0. If I were just setting this equal to 0, what did we do in chapter 5 when I had a quadratic equation where A was not equal to 1? Did we factor it? No, what did we do? Quadratic formula, right? We just used the quadratic formula, which I could do here. I could do that. If this thing were actually equal to 0, to solve this, all I would have to do is use the quadratic formula, but instead of x equals, it'd be x squared equals negative b, plus or minus, etc., right? We would have gotten x squared equals negative b, whoops. Negative b would have been 5 plus or minus square root b squared would have been 25 minus 4 times 6 times negative 6, all divided by 2 times 6 would have been 12, right? And then I'm just going to, I'm going to zip through this real quick because we're going to actually factor this in. I'll show you how to factor it, or remind you how to factor it. But if I simplified this whole thing, I just would have gotten x squared equals 5 plus or minus, that whole thing's going to add up to 169. 25 plus 144. Just trust me on that. And then over 12, and so I'm going to get two answers out of that. I'm going to get the plus version and the minus version. If I simplify those, and you could do this stuff, and you can watch the other YouTube video if you want to see it, I'd get either x squared equals, if I take the plus version, I'm going to get the answer, that's going to all simplify to 3/2. If I take the minus version of the quadratic formula, I'm going to get x squared equals negative 2/3, and then all I have to do is square root both sides, and I get 4 solutions, right? Does that make sense? So I'd get x equals plus or minus the square root of 3/2, or x equals plus or minus the square root of 2/3 times I, right? Because I've got that negative. Okay? And so we could, if it were equal to 0, that's pretty easy stuff, right? That's not that big a deal, but unfortunately, it's not. Unfortunately, we've got this equation, or we got this expression that we're trying to factor. So let's just deal with that. How do we deal with that? Okay, well this is an A times C then split B issue, isn't it? If we're going to factor this. So I got it, what is A times C? Okay, so AC equals negative 36. What are two numbers that multiply to negative 36 and add to negative 5? No, I would multiply to negative 36. Negative 9, positive 4. Very good. So I can split this up into negative 9, positive 4. So that's how I'm going to split B, right? And so I would end up then with, split this thing up into 6x squared minus 9x squared plus, right, I'm gonna split that b term up. Remember this stuff? Plus 4x squared minus 6. And now, we just factor by grouping, which we just did. Right, I'm just gonna group the first two together and the second two together and factor by grouping. What's the biggest common factor from the first group? I can take out a 3x squared, leaving me with what? 2x squared. Everybody see that? Because 3 times 2 is 6, and x squared times x squared is x squared squared, right? Minus 3, very good. Okay, plus. Now this time, I know that factoring by grouping has to work because we found magic numbers. So I know that that is definitely, that is definitely going to give us a leftover of 2x squared minus 3. What's my greatest common factor have to be? 2. Okay. So then we end up with, I can factor out the blue factor, the 2x squared minus 3. Factor out, and then what am I left with?
3x squared plus 2.
3x squared plus 2. Okay, and can I go any further with those? I can't I? Because this one, if I could go further, that's a 2-term polynomial. I'd have to use a pattern. The only pattern that would work there is a difference of squares, but I can't write 2x squared as an integer. I mean, that's just not, it's not going to conveniently fit into that pattern. And this one, the second one, the only pattern that it could ever fit would be a sum of squares, which is no pattern, right? So we'd be done there. Okay? Make sense? Okay, good. Let's go to 205.
Andrew, come on back.